So I'm Effie, and today I want to talk to you about Android internals for developers. And what I mean by that is that I want to give an overview of the Android operating system for developers who just are unfamiliar with it or don't know what happens with our apps at all. I work for Pinterest, and let's start. So the first thing that people always say about Android is that it's based on Linux. And Linux is an open source operating system that is made for computers and not for phones. And it has many distributions, many different flavors. So the question is Android also a Linux distribution? So the answer is no. Android is based on the Linux kernel, but it also made a lot of modifications and greatly deviates from Linux coming off the kernel level. So it's not really a Linux distribution. It's only based on it on a very small subsection. So as we go over the basic Android architecture, these are the main components that I will cover in this talk. Up there are our apps that we run, that we build and develop for. And I'm going to start with the bottom and start by speaking about the kernel. So what is a kernel at all? A kernel is a computer program that is basically the core of a computer's operating system. It has a complete control of everything that happens inside of the system. It's the first program to be loaded on startup, and it handles the rest of the startup process. It handles your CPU. It handles the memory. It also manages input-output devices, and it communicates with other processes in the operating system through something called system calls. System calls are being done by other processes when they want to do things that are, for example, hardware-related, like get something from an input-output device, or create or execute a new process, or communicate with integral kernel services, like process scheduling, or things like that. And what is a process? A process is an instance of a computer program that is being executed. So going back to our kernel, the Android operating system, like we said, is built on Linux. And it's built on Linux kernel. There are significant modifications that have been made to the kernel, but it is essentially the same core. It is essentially the same CPU management, the same memory management. All these things are imported as is. The reason is that it's working. And these things are the same between phones and between computers. And also that it's open source, so it's easy to take from, it's easy to modify and update, etc. We know that whatever the kernel is doing on a computer, like I said regarding CPUs and memory, works. And we know that the permission-based security model also on Linux also works well. So it's great to use. However, the Android did make a few modifications. And these modifications are because this is a phone and not a computer. A phone is not connected to power all the time. A phone needs to be able to stay alive even when it's like sort of dormant in a way. And so Android is making a bunch of modifications on top of the Linux kernel. And I'm going to mention two important ones. The first one is the out-of-memory killer. The out-of-memory killer is a process run by the kernel, and that was created for a bunch of reasons. The first one is that users don't typically kill apps. They open a bunch of apps, they navigate between apps, but there's no like X button that they are implicitly required to do in order to close up a process. The other thing is that Android runs on low-end devices. They have typically less memory and less tricks to use more memory. Linux has a bunch of tricks to do when it runs out of memory. But Android was designed to run without any of that. And Android needed a way to say, I will clear out memory before it runs out to a catastrophical level, before I want to try to allocate something, and oh my God, there's nothing there. So Android was trying to be smarter about calculating beforehand how much memory we have available. Have we reached some sort of watermark? Are we reaching some sort of watermark where maybe in the future we will need that amount of memory? And clearing out processes that are least used or less used in order to free up that memory for other apps to use. So Android wants to be smart about these rankings and ranking these processes. And here I just pulled out a list of processes that are arranged by order. The important thing that I marked in a little circle is that right now we have 30 processes running. And in this example, a few minutes later, I opened up my camera and started taking a bunch of pictures. And lo and behold, I lost a bunch of processes. Why? Because what I'm doing right now is very memory consuming. And I reached one of those thresholds to tell the kernel, please clear out some of the processes that have been unused or not important. The second important modification to the kernel is the wake locks. So computers are awake all the time. And when you close them, they're really, really closed. They cannot receive notifications or phone calls or do these kind of things. But we cannot keep a CPU running on a phone all the time because we're just going to run out of battery. So what Android does is it tells something else. If no one is actually performing an action on my CPU right now, turn it off. Turn it not really off, make it sleep. Make it consume as little energy as possible. And if nobody's holding a wake clock, nobody's performing any operations, like I said, go to sleep. So this is normally the normal state that you will see on your phone at any given moment, unless, like in brief seconds, I don't know, network calls are being made or a new window is being drawn. But most of the time, this is what you should be seeing when querying the wake locks. But for example, if I'm playing a video, which is something that definitely needs to keep my device awake, I will see that now I have 2 wake locks that are being held, one for audio, one for video, for the video that I'm playing. These are just the 2 things that I thought most important. There are a bunch of other modifications made to the kernel, but these are just like the main 2 important ones that I thought to bring up. The next step in our list of architecture components is the init. The init process is a binary that's picked up by the kernel and being run on startup. It's the first user space process. It is also the root of all other processes. All other processes will be created from this process. And it spawns everything else in the system. It's basically just a list of instructions and settings about what other processes to wake up and give them special, I don't know, you should do that, or you should be configured in that way. Most of the things that init will start up are called daemons. Daemons are processes that will run in the background. The user will not interact with them. They will not know they exist. They cannot communicate with them or be even, I don't know, like tell them to do anything. I named some of them here that might look familiar to you, like ADBD or install-D that's being used to install apps. And in the biggest circle, I put the next one that I'm going to talk about, which is the Zygote. So the Zygote is a special process. It's a special daemon. It's the base of all other Java-based applications, or Kotlin. And it contains a ready-to-go runtime environment or virtual machine ready to run our app. So what does that mean? We write Java code. Our Java code is being pre-compiled, it's being changed, it's being managed by someone, and then it's being run by some sort of an environment. We know this as Dalvik or Art. And this environment has things like garbage collection and some memory allocations, heap, stack, etc., and some classes to manage that. And all these things exist within Zygote. It has basically an environment that's ready to go and is just like, give me an app to run, give me Java code to run, I'm ready to start running it. It has the Dalvik or Arts environment, it has some preloaded resources, and it has some preloaded classes. And why is that good for us? It's good for us because now when we want to start running an app, we don't have to pre-initialize all these things. We can say, we are just wanting to run that Java code. This environment is ready to go. So that saves a lot on startup time. And another thing is that some of these resources and some of these classes are shared, so they can actually use the same memory and reduce the memory footprint of our apps. Now, in Linux, traditionally, processes are being started by using two commands. The first one is fork. Fork is take a parent process and create a child process out of it. The second one is exec, which means in the child process, because it is now identical to the parent, erase everything that was on there, it belonged to the parent, and please start executing a new code, something that we want, a new process, a new app. Zygote is using fork, but is not using exec. And what does that mean? It means that we get an identical process from Zygote, and now we can just put our app code in it. And if we want to fork another process in the future and run another app, again, we have the entire environment ready to go and ready to start our app. And I'm sure everybody has seen this exception in a crowd before. And this is just to tell you that I'm telling the truth. And all our processes and all our environments initially come from Zygote. And it is the thing responsible for running our app, basically. Usually in Linux, apps run under the same user, the user being me or you or an admin or something like that. Apps that run that way on Linux can share a bunch of resources. They can share memory sometimes, they can share files, and Android decided that this way is not for us. They said, we want to create a separate sandbox for every process, for every app that is running on the phone. And the way they do it is they pretend every app is a user. Every app gets its own user ID, or UID for short. And that way, the apps cannot talk to each other. They cannot, corrupt each other's memory. They cannot write into each other's files. That is one of the things that make Android very secure. So that was why this way was chosen. And again, just a list of processes that I pulled off my phone. And on the far left, you can see the IDs of users, which are all different. And now, you may ask yourself, OK, this is very cool. But apps do need to communicate with each other sometimes. Like, it's a thing. They need to be able to talk to each other. We just said they can't. What do we do? And this is where something called the binder comes in. The binder is there for processes, for different apps to communicate with each other and to make sure that we can do it in a safe way. I pulled off some code that I'm pretty sure will be familiar to many developers. It's the connectivity manager. We are basically getting it from something called system service. And we are asking, please get the active network info. I'm sure a lot of you have done that before. So the first thing that I want to say about this is, why can't we do it in our code base, right? Why can't we, for example, be the ones that query for network info? I mean, why can't this code just live in our app? I mean, and then the answer is, this code is probably doing some complex things, such as asking the Wi-Fi driver or asking other hardware components about their situation. And if we were to do it in our app, in our process, that means that our app and our process would need all these permissions to actually talk to all these components. So putting it away in a centralized service makes more sense, because that service will have all these permissions while we don't. Now, say I'm the curious developer, or for some reason I encounter a bug and I want to see the source code of this method. So I navigate into this method, and this is what I see. It's a wrapper around an interface. This isn't helpful. It's not really code. It doesn't tell me anything about what is the actual implementation of this method. So I dive a little further. OK, I have the IOSP source code. I can look into it. What is this interface? OK, it's an interface. Cool. What's going on? The answer is that while this may have seemed like we call a method, we're actually not speaking directly to the activity manager. We are actually going through something called a binder. And how would that look like? Our app is not directly talking to the other app. It's actually going through all this journey, all the way down to the kernel, and then up again to send our message and come back with the result. So a lot of the heavy lifting for this process happens in the kernel. The kernel gets a message through a system call. And the kernel is the one responsible for saying, yes, I can deliver this message. I know who the recipient is. Or no, I have no idea what you just asked for. Sorry, no luck. It's also responsible for maintaining that list of handlers who asked for what, and knowing that when a process dies, all the handlers that are attached to it should also go away or receive some errors because it no longer exists. It's basically your average mailman in that case. The problem with this is that, I mean, you can't really Java system calls. Like, you can't be like, OK, I want to system call a message to the kernel binder model, which is where the Binder.java class comes in. The Binder.java class has two main methods, I would say. The transact is on the sender. The sender will call transact, and the recipient will get the on transact. Now you can see it passes a bunch of things, such as a certain code, a parcel, which is all the data, maybe the method arguments that we wanted to send. A reply could be whatever got it as a response. And again, on the recipient side, we would open these up, see what we got from there, and figure out what we want to do with it, what maybe actual code we want to call with it. Now, technically, we can call transact and on transact, but we will spend a lot of time creating those parcels and creating those codes, creating that in a way that the other process will understand. And then we might spend a lot of time, if we're the recipient, opening up different messages or figuring out how to open different messages, where to direct them, what actual method we want to call in the end, because we want to call an actual method. We don't want to call a package. We don't want to send just a message. We want to perform an action, perform an actual method call somewhere along the way. And this is where the AIDL tool comes in. And it serves as a bridge between the actual method and a transaction. And it auto-generates a lot of code, all the parceling and all the marshalling and unmarshalling parts. And it generates two parts. One is the proxy, which is the sender. And one is the stub, which is the recipient. So this is an example of how the proxy would look like. It's a lot of, I don't know, boilerplate coding that I would assume nobody would enjoy writing. In the middle there is the transact method, which is the actual binder. Please perform this transaction with this data, etc. And on the receiver side, we are overriding on transact to receive the actual transmission, open it up, figure out what was the actual method I wanted to be called, and call it by calling this getActiveNetwork. That actually will call the real method, the real implementation of this method. So this is the real implementation. Connectivity service is extending the stub, and this is the actual code. We made it all the way. And then going back to our initial method call and thinking, so wait, what do I actually have there on my sender side? And the answer is we have the proxy on our sender side. So looking at this all the way through again, app1 is calling some interface in app2's method. Then it passes through the Java interface classes and calls transact on the binder class. The binder class translates this into system call. It goes to the kernel. The kernel figures out who should receive this message, and then calls a system call to the binder on the app2's instance. This binder calls on transact, and the Java interface classes, our stub in this case, will call the actual objects method. The last part of my talk is the system server. The system server is the heart of Android. Is really responsible for all things Android. It's one process. It's written in Java, which is why I have this little arrow coming from Zygote to it. And I added another arrow because Init is the process that is telling Zygote, please fork yourself, create system server, run the Java code for system server on this new instance of yourself. It has a lot of managers that I will only go through a few of them. It really has a lot. It has a lot of managers, and they all live in the same process. And the three most important ones, or at least from my perspective here, are the activity manager, the window manager, and a package manager. So the window manager, as its name applies, is responsible for windowing and being in charge of all things Windows. It keeps track of Windows activities. It keeps track of what is visible and what is not. It is responsible for transitions between activities and for an overall good UI experience, for example, on cases of configuration change on rotation. And it is responsible for system-level gestures, which basically means if my app didn't handle a certain tap or a certain gesture, it bubbles up until it reaches the window manager. The other thing, the next component is the package manager. The package manager is responsible for installing new applications. It's responsible for resolving the correct activity in case I sent out an intent and I want to know which activity to actually start up behind that intent. And in case it's an implicit intent or there's more than one, it creates a list of possible activities and then launches a special kind of activity called like an activity chooser to choose which activity to launch. And the last manager that I wanted to talk about is Activities Manager. Activities Manager is the heart of of Android. It is really sort of like the God object of all things Android. It is responsible for everything, all the activities that we create, and the name is not, I guess, good enough because also for all the services, all the content providers, everything that we create in our apps as developers is being managed by the activities manager. So like I said, it's responsible for managing applications, services, content providers, you name it, it's all there. It's managing life cycles. This is the one that's going to make all the decisions about which app is resumed, which app is stopped, which app is, I don't know, paused. Pick another state. It is responsible to manage the actual user, not to be confused with our fictional user IDs before. We actually have a real user using the phone. It's responsible for memory trimming. We'll see a little more about that in the future, but also sometimes it would intervene if something really bad is going on and be like, please kill it. This is this thing has gone rogue. And it also handles configuration changes and is responsible, for example, for restoring the correct activity or restarting the correct activity in case we changed our phone's orientation. Now, applications are managed in the activity manager in some sort of a tree. And it starts with a stack. And a stack is basically just a bunch of apps that are being pulled together. For example, if we have split screen, we will have 2 stacks. And in the stacks sit multiple tasks. There are many exceptions to the process 1 that I put there. We'll see a little bit more about that. But for simplicity, yes, mostly a task will be for one process. And under a single task can sit activities, usually the activities that belong to the same app. So let's talk a little bit more about processes and activities. Technically, every app, like we said, sits in a different process. But all activities that are going to be created for that app are going to be created in the same process. So in this very simple example, we have Activity Manager monitoring one app, so it has one task, and it keeps records of all the activities that it has. This is the activity record, and what state they are, in this case resumed, because it's the top activity. It's what we're doing right now, I guess, what the user is doing. And in our process, we will have one main activity. If I would add another activity from it, say navigate in my app from my main to like any secondary activity, another record would be added to the same stack, another activity would be added to the same process, and the states have changed because now we have the secondary app activity resumed, and the one below it is no longer active. If we were to add another app, say the user picked another app to start, now we have a new task with a new activity record, and we would still have the old one, it would just be below it. Now this is where I said things get a little tricky, because for example, if from within my app, I would want to navigate to or start an activity of another app. Say the most obvious case is the case of sharing. I would open another activity that belongs to another app. It would be in my task, but it would be in the other app's process. It would not live in my process. So like I said, the main functionality of Activity Manager service is to manage the lifecycle of all our apps. The one top rule that they have is there could only be one resumed app at all times. There can never be more than one app resumed at all times. So split screen, for example, will have only one resumed app. picture-in-picture mode, for example, will be paused always. Only one resumed app at all times. It is also responsible for telling Window Manager, for example, to create a surface for an app, or remove a surface for an activity, or I don't know, it became visible or invisible. It's also responsible of assigning thread priority and CPU affinity to activities and to processes that they run in. It can take or give permissions to certain activities. An activity that is stopped cannot do a bunch of things. It cannot, I don't know, open the phone and start open the camera and start taking pictures. It's stopped, so it loses that permission. And it makes the out-of-memory adjustments. So going back, you remember I told you that the kernel has an out-of-memory killer that wakes up at certain thresholds and kill a bunch of processes. But what the kernel doesn't know is how important a process is. It has no way of judging whether this has an activity. It's totally abstract to it. It doesn't even know what activities are. It doesn't know which one of them the user is interacting with right now. It doesn't know which one of them is important or not important. So it is the responsibility of the Activity Manager service to actually do these adjustments and set up something called an out-of-memory value to each and every process based on what it knows, because the Activity Manager knows. It knows which activity is resumed, which activity is paused, etc. So going back to that list of processes, they are sorted, like we said, by out-of-memory values. And there are several categories that we can see here that mark the importance of these processes. So the top process would always be system. And then persistent, which are things like system UI and phone, things you don't want to lose. Under that is the foreground. That's the app that's been resumed right now, the activity that's been resumed, whatever the user is actually seeing and interacting with right now. Under that is visible, maybe things that are partially visible or things that are somewhere there and could be visible by the user. Under that, it's perceivable. And it goes on and on. There's a bunch of other categories here, but I guess you get the point. And in Activity Manager Service, there are two methods that are apply, adjust locked, and computed. And those are the methods that are going to get called basically whenever anything changes. Whenever any activity gets created, resumed, stopped, whatever, everything, this will get called. And the kernel will be notified of the new adjustments. It's a little complicated too, because, for example, services may get a lower priority, but if they are running, for example, music, they are perceivable by the user, they should get a bump, so they will not get killed. And then the other thing that happens is that the Activity Manager service is listening and getting back the notification from the kernel in case it killed processes. And then the Activity Manager service goes and cleans out all the activity records that existed and cleans out whatever information it had about these processes. So let's start going through a flow of starting a new activity. I'm going to go through a very, very basic flow. There are a million things that are being done in the process of starting a new activity. It's incredibly complex. There are a million edge cases and decisions and ways this can be done. So I'm just sticking to a very basic flow of we have a new activity, we have, say we don't even have a process for it, and how does it happen? So the first thing is Activity Manager service will get called with the method start activity as user. And inside of it is another call start activity may wait. And in start activity may wait, the first thing that will happen is we need to know what activity we want. And for that, we will call the package manager. The package manager on startup, when it first gets created, parses through all the application manifests, all the things that we write, and picks up from them all the activities, receivers, services, everything we wrote in there, and it holds it all in memory. It has a huge in-memory structure of all these intents that we created. And it goes through all this list and figures out what we want. And it has two different ways to do it based on whether we actually know what activity we want, in which case we can call getActivityInfo, or we don't, it's an implicit intent, or it's, I don't know, like some sort of a URL. And then it will go to resolve intent and bring back one or more relevant intents. And a special activity will get invoked if it's more than one activity that can match our filter, which is the activity chooser. Say for our sake of simplicity, we found one activity. We're going on with a very simple case. The next thing will happen is we'll create an activity record for it in Activity Manager service to keep record of our activity and whatever state it's in. State 3 is not actually one step. It happens throughout the creation of a new activity. I just wanted to put one example of it here. Throughout the process, we'll communicate with Window Manager and tell it, create a new window for me, create an app transition for me, do the things that Windows do for the user to be able to see and perceive my app. The next step is resume the top activity. Now that we have it, and we assume, again, the user clicked on it and you actually want to see it, it needs to switch to state resumed and be active. And that's when we decide, do we actually have a process for it already? And if we do, we'll use that. We'll just add the activity to that existing process. If we don't, we'll create a new process by calling a method called process start. And in process start, we will start a new process by forking Zygote. So going back to the forking of Zygote, this is where the magic happens. This is the method call that will call a native call, please, Zygote, fork yourself, and let me know when you're done. Activity Manager service is listening to the callback from the new process. Once the new process have started and finished forking, it will call back home and say, hey, I'm ready. Please tell me what to run. And then Activity Manager service, it's listening on a special port, will be like, oh, hey, let's figure out what activity I actually wanted to run, and then bind that application, run that code in my new process that's ready to go. So that's it. That wraps it all up. Thank you all for coming and listening to this journey. And I want to thank basically all the Googlers I know in the world. And any questions? Yeah.
So when you call something like the get network method, where does that get executed? Is that a different process? Or?
It gets executed in the system service, which is a different process, yes.
And that gets forked from Zygote?
Yes. Surprisingly enough, even though all the managers that I said exist together in system server, they will also often call each other via the binder mechanism. All right, thanks. I'll be around if you need more, if you have more questions.